Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. Welcome to the Stack series. Today we are exploring the hidden geometry of reality.
And it is genuinely a thrill to sit down for this. This comprehensive look at the material you send our way is, well, frankly, it's paradigm shifting.
It really is.
We are asking a massive question for you today. What if the exact same mathematical blueprints that dictate the shape of your DNA also determine the architecture of our greatest buildings, the physical structure of sound itself, and this is the wild part, even the fundamental fabric of quantum particle interactions?
I have to admit, when I first looked at the stack of research we pulled for you, I was a little overwhelmed.
Right, it's a lot of ground to cover.
It's massive. We are looking at Samit Kumar's mind-bending work on a quantum geometric structure called the amplituhedron that we completely pivot into cosmological studies on the Poincare dodecahedral space.
Which is a wild theory.
Completely wild. A theory about the actual physical shape of the entire universe. And then we have architectural research on biomimetics, plus the acoustic philosophy of the legendary composer Yannis Xenakis.
Yeah, pulling from physics, biology, architecture, and music all at once.
Exactly. So our mission today, our in-depth exploration, is to figure out the invisible thread that ties all of these seemingly disparate fields together into one cosmic code.
To find that thread, we really need to start with the foundations. We have to look at what we think we already know about the mathematics of nature.
Because before we can jump into the shapes of the universe.
Right, or the geometry of quantum mechanics.
Yep.
We have to understand the math that is literally growing in your backyard right now.
Okay, so for anyone listening, you've probably heard of the golden ratio. We see it in art class. We hear about it in Da Vinci's work. It's roughly 1.618 to 1.
Yes.
And it's intrinsically tied to the Fibonacci sequence, which is that famous string of numbers where each number is the sum of the two before it. So 1, 1, 2, 3, 5, 8, 13, and so on.
Which is such a simple rule, but it scales infinitely.
Right. And if you divide any number in that sequence by the one right before it, you get closer and closer to that golden ratio.
Yeah.
But the sources make a major point to say this isn't just an abstract math concept invented by Greek philosophers.
No, not at all. It is a physical, structural imperative. Nature is remarkably lazy, or, well, rather, incredibly efficient. The golden ratio allows for the absolute most efficient packing of physical information.
So it's about saving energy.
Exactly. That's why you see it dictating the spiral of a nautilus shell, the arrangement of seeds in a sunflower head, and even the massive atmospheric swirl of a hurricane. It allows systems to grow outward without ever changing their fundamental shape.
That makes sense for a sunflower. But the most stunning detail from the research regarding this ratio involves the very instructions of life itself, our DNA.
Yes, the bDNA molecule.
I wanted to ask about this because it sounds almost too perfect to be true. What is it about the physical dimensions of DNA that connects to this math?
So bDNA is the most common form of the double helix found in our cells. If you were to measure the physical dimensions of that helix under a scanning tunneling microscope, you'd find that the length-to-width proportion of a single full 360-degree turn of that helix follows the golden ratio.
A single turn.
Yes. Specifically, one full turn measures about 34 angstroms long, and the molecule is about 21 angstroms wide.
Wait, 34 and 21. Those are literally successive numbers in the Fibonacci sequence.
They are, and if you divide 34 by 21, you get 1.619.
Which is astonishingly close to 1.618.
Unbelievably close.
Is that just a coincidence? I mean, human brains are wired to find patterns even when they aren't really there. Or we just, I don't know, overlaying a math equation onto a biological molecule because we want it to fit our theories?
That's a highly critical question. It's one scientists ask themselves constantly. But in the case of the golden ratio, it's not pareidolia, it's thermodynamics. Well, at the molecular level, DNA has to fold, twist, and pack itself into incredibly microscopic spaces within the cell nucleus, all while remaining stable and readable by enzymes. The geometric proportion of 34 to 21 angstroms provides the optimal structural integrity.
So it's structurally necessary.
Right. It actively minimizes the energy required to hold those molecular bonds together. So life didn't choose the golden ratio because it's visually beautiful. It chose it because it is the ultimate path of least resistance.
Which totally makes sense as to why humans have been obsessed with these geometric shapes for millennia. The sources spend quite a bit of time on ancient sacred geometry. Shapes like the torus and the flower of life.
Yes, the fundamental shapes of esoteric tradition.
What exactly is a torus, structurally? Like, how would you describe it to someone listening right now?
Visually, you can picture the torus as a donut or an inner tube. But dynamically, you have to imagine it in continuous motion. It is a continuous, self-reflexive loop of energy. Energy or matter flows in through the top center, circulates down around the outer edges, and gets pulled right back up through the bottom center.
Like a smoke ring.
A smoke ring is a perfect, observable, physical example of toroidal flow. It is a system that perfectly sustains itself. And we see this geometric blueprint at massive scales. It's the exact shape of the Earth's magnetic field, which acts as a protective shield against solar radiation.
That donut shape surrounding the planet.
Exactly. We see it in the structure of certain galaxies, too. And interestingly enough, in many esoteric and spiritual traditions across the globe, the human aura or electromagnetic energy field is described precisely as a torus.
It's the ultimate shape of balance.
Yeah.
A self-sustaining loop. And then there's the flower of life. I know I've seen this pattern everywhere, from ancient Egyptian temples to modern geometric tattoos.
It's very popular visually.
It's that intricate figure made of evenly spaced, overlapping circles that form a sort of hexagonal flower-like lattice, right?
Yes. And the flower of life is fascinating mathematically because it acts as a geometric matrix. The overlapping circles map out the fundamental nodes of physical space. And if you connect certain intersections within that two-dimensional pattern, you derive Metatron's cube.
Okay, Metatron's cube.
Right. Now, Metatron's cube is highly significant because it contains the two-dimensional blueprints for every single one of the Platonic solids.
Just to clarify for our listeners, the Platonic solids are the fundamental 3D shapes. The tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron.
Correct. They are the only regular convex polyhedra in existence where every face is the exact same regular polygon, and every single vertex has the exact same number of faces meeting at it.
It's geometric perfection.
It is. Ancient cultures universally understood these shapes as the fundamental building blocks of solid form. The math doesn't allow for any other perfectly regular 3D solids to exist.
Okay, so I can wrap my head around solid forms. I can picture a cube or a donut or the double helix of DNA. But the research transitions from physical, solid geometry to something completely invisible. Sound.
Yes. Acoustic geometry.
I have seen videos online of people putting sand on metal plates, running a violin bow across the edge, and the sand magically forms into perfect geometric shapes. Is that what the sources mean by cymatics?
That is precisely the foundational experiment of cymatics. Ernst Chladni pioneered this back in the 18th century, and Hans Jenny drastically expanded on it in the 1960s. Cymatics is simply the study of visible sound.
But how does a squiggly sound wave organize raw matter like sand?
To understand how it works, we have to look at the physics of a standing wave. When you vibrate that metal plate, say with a violin bow or an electronic oscillator, the sound wave travels through the metal. As the waves bounce back and forth off the edges of the plate, they cross paths and interfere with each other.
Like ripples in a pond bouncing off the edge.
Exactly like that. And this creates what we call a standing wave. Within that standing wave, there are areas vibrating violently, which are called antinodes, and areas that are completely, perfectly still, called nodes.
Ah, so if I'm understanding this right, the sand isn't actually moving into the shape.
Right, it's being aggressively bounced off the vibrating parts of the plate until it falls into the quiet, still zones, the nodes.
That's a great way to visualize it. The sand just seeks the areas of least resistance.
It does. But what's incredible is the geometry of those nodes. It provides physical, irrefutable proof that vibration intrinsically organizes matter.
And there's a pattern to it, right?
Yes. The specific correlation observed by Hans Jenny is that low, deep frequencies create simple, large geometric shapes. You might get a basic circle or a simple cross, but as you raise the pitch, as the frequency becomes faster and more energetic, the nodes multiply and complexify.
Right. The patterns become incredibly intricate. You go from a simple circle to these jaw-dropping, fractal-like structures, complex mandalas, and perfect hexagons.
It happens instantly.
It's like watching reality act as its own digital visualizer, organizing physical matter in real time. But how does that apply to the human-made spaces we live in? I mean, you and I aren't living on vibrating metal plates.
But we are living in acoustic chambers. Every room you enter is an acoustic chamber. Architecture is deeply tied to this geometry. The ancient Greeks intimately understood this. Their open-air amphitheaters utilized precise geometric grading to carry a single human voice flawlessly to the back rows without any electronic amplification.
It's always amazed me you can drop a pin on the stage and hear it in the back row.
Because of the math. And this isn't just lost ancient knowledge. Acoustic engineers today rely on this exact same math when building modern recording studios and concert halls.
The sources give a really fascinating specific example of this that I want to dig into. Because if you're trying to build a perfect acoustic room, say a multi-million-dollar recording studio, you can't just build a big drywall box.
If you build a standard symmetrical box, you create an absolute acoustic nightmare. Sound waves will bounce off parallel walls and crash into each other.
Creating those standing waves we just talked about.
Precisely. They will create constructive interference, which artificially boosts certain bass frequencies so they sound muddy, and destructive interference, which creates dead spots in the room where certain sounds entirely cancel themselves out.
To prevent that, the sources say acoustic engineers use the golden mean. Can you walk us through the actual math of building that room, like the physical dimensions?
Absolutely. The math dictates the volume and proportion of the space to ensure sound dissipates naturally without bunching up. The source provides an optimal blueprint. Say you are constrained by a standard 10-foot ceiling. You apply the golden mean ratio to derive the other two dimensions.
Okay.
For a 10-foot height, the absolute optimal acoustic width is exactly 16 feet, and the optimal length is 23 feet 3 inches.
So the entire room is essentially a three-dimensional manifestation of the golden ratio.
It is.
The math that dictates how a sunflower packs its seeds is the exact same math that prevents sound waves from clashing in a recording studio. That is beautiful.
It's the geometry of optimal flow. But of course, while we can confidently measure a recording studio or a strand of DNA, science is never entirely settled when it comes to the macro scales of reality.
Right. And this brings us nicely into our second phase today, the active debate, where science currently disagrees. Because if the universe mandates these geometric rules for sound, DNA, and architecture, what about the geometry of the universe itself?
That is the ultimate question.
For a long time, the standard textbook answer for the shape of the universe was that it was flat and infinite, Euclidean space, like a piece of graphing paper extending forever in all directions. If you draw two parallel lines, they will stay perfectly parallel for eternity.
That was the widely accepted model, but that assumption is currently the subject of an intense, highly technical debate involving three manifolds and topology. Cosmologists are actively arguing over isotropic geometries.
Let's slow down for a second. Isotropic.
Isotropic simply means the space looks roughly the same in every direction, no matter where you are looking from. There are three primary geometric candidates for the universe.
Let's break those down because the terminology gets heavy here.
First, we have E3, which is the flat Euclidean space you just mentioned. Then there's H3, which is hyperbolic space. You can visualize hyperbolic space as being shaped somewhat like a saddle.
A horse saddle.
Yes. In H3 space, if you shoot two lasers perfectly parallel to each other, the geometry of space itself will eventually cause those two beams to diverge and bend away from each other.
Okay, and the third option?
The third is S3, or spherical geometry. In this space, the universe curves back in on itself. If you shoot those two parallel lasers, they will eventually converge and cross paths.
Which brings us to the Poincare dodecahedral space, or the PDS model. This is where the research gets incredibly wild for me. This model suggests the universe is not flat. It falls under the S3 spherical geometry category, but it proposes that the fabric of space is formed by tessellating dodecahedra.
To help visualize this, remember the Platonic solids we discussed earlier. A dodecahedron is a 12-sided solid where every face is a perfect, identical pentagon. Think of a standard 12-sided die used in tabletop games.
Okay, but what does tessellating mean in a 3D context? I know bees tessellate hexagons to make a 2D honeycomb without leaving any empty gaps between the cells. How do you do that in 3D?
It's the same underlying principle. You cannot perfectly tessellate spheres. If you stack basketballs in a box, you always have empty space between them.
Right.
But in hyperbolic and spherical geometries, you can take a central dodecahedron and perfectly fit other dodecahedra onto all 12 of its faces, locking them together like cosmic Lego blocks without any gaps.
Wow.
The PBS model posits that if you tile 120 of these dodecahedra together, they fold in on themselves to create a closed, finite, yet boundless universe. It is formally known in topology as a Poincare homology sphere.
Okay, wait. Finite but boundless. That sounds like a contradiction. Let me try an analogy here to see if I have this right.
Yeah.
Is it like the classic arcade game Asteroids?
Oh, that's a good comparison.
Because when you fly your little spaceship off the right side of the screen, you don't crash into a physical wall. You instantly reappear on the left side of the screen, still moving in the same direction. The space has a set, finite limit the size of the screen, but you can travel boundless through it forever.
That is a phenomenal way to understand it, yes. In a Poincare dodecahedral space, if you were to get into a hyper-advanced spaceship and travel in a perfectly straight line for tens of billions of light years, you would eventually loop back around and arrive right back at your starting point on Earth.
That's incredible.
You would navigate the entire volume of the universe without ever finding a physical edge or a wall.
But how could we possibly prove that? We can't travel billions of light years. Are cosmologists just doing math on whiteboards? Or is there actual physical evidence for this 12-sided universe?
They are actively looking for the evidence, specifically within the cosmic microwave background, or CMB.
The CM.
Yes, the CMB is the primordial radiation left over from the Big Bang. It's essentially the thermal echo of the universe's birth, captured when the universe was just 380,000 years old. Satellites like WMAP have mapped this background radiation across the entire sky. It looks like a giant, modeled sphere of slight temperature variations.
And what do they find in those temperature variations that suggests a dodecahedron? I mean, how do you see a shape and temperature?
They found a glaring anomaly called the suppression of the CMB quadrupole.
Okay, stop right there. Suppression of the CMB quadrupole sounds terrifyingly complex. Break that down for me.
It does sound complex, but think of the early universe like a ringing bell. When you ring a large bell, it vibrates with many different frequencies simultaneously, high pitches and low, deep bass notes.
Right.
In cosmology, the quadrupole represents the absolute largest spatial waves, the deepest bass notes of the universe's temperature fluctuations. If our universe were truly infinite and flat, there is no physical limit to how large those temperature waves could be. We should see massive, vast thermal fluctuations spanning the entire sky.
But we don't.
We don't. The WMAP data clearly shows that the largest waves are simply missing. They are suppressed. The deep bass notes do not exist.
So, using the bell analogy, the reason those deep bass notes are missing is because the bell itself physically isn't big enough to resonate at those frequencies.
Precisely. A finite, closed space, like the Poincare dodecahedral space, naturally suppresses those largest wavelengths because a wave larger than the universe literally cannot fit inside the cosmic geometry. The geometry itself acts as a physical filter.
That is incredible. And the sources mentioned scientists are looking for something called circles in the sky to confirm this. What are those?
Yes, the field is known as cosmic crystallography. If the universe is a finite space folding back on itself, like your asteroid screen, then light from the early universe has had enough time to wrap entirely around the cosmos.
Meaning light has done a full lap.
Exactly.
Yeah.
This means we should be able to look in two completely opposite directions in the sky and see the exact same thermal patterns from the CMB.
We'd see a duplicate of the universe.
Right. Because of the spherical geometry, these matching patterns would appear to us as intercepting circles. We're essentially looking for duplicate images of the same ancient light, just viewed from different angles in a massive cosmic hall of mirrors.
So we're literally scanning the edge of the observable universe, looking for the seams of the dodecahedron. We haven't definitively proven it yet, but the fact that the geometric structure of a 12-sided die might be the blueprint of the cosmos shows how deeply this ancient math permeates reality.
It does. But this active debate over geometry isn't isolated to theoretical physicists gazing at the stars. It happens right here on Earth, particularly when we evaluate the legacy of visionaries who tried to forcefully apply these cosmic geometries to human society and engineering.
Which brings us to a really fascinating, highly debated figure, our Buckminster Fuller. For those listening who aren't familiar with his work, Fuller was a mid-20th century architect, systems theorist, and inventor. He is the pioneer who popularized the geodesic dome. If you've ever seen the spaceship Earth structure at Epcot in Florida, that's his geometric child. He also championed tensegrity structures.
Tensegrity is a brilliant application of geometry. Instead of building massive, heavy walls that rely entirely on stacking weight for compression, tensegrity uses a synergy of isolated components in compression, like rigid wooden or metal struts, suspended inside a continuous net of tension, like cables.
So the parts aren't just squishing each other.
No, it distributes stress perfectly across the entire geometry, allowing for structures that are impossibly light but incredibly strong.
But his legacy in the scientific community is surprisingly polarized. The sources highlight an active debate regarding him. Was Buckminster Fuller a genuine visionary who delivered great gifts to humanity, or was he largely an incomprehensible, eccentric performer?
The debate stems largely from his communication style. Fuller was famous for delivering absolute marathon lectures. He wouldn't just give a highly polished 45-minute TED Talk. He would stand on a stage and speak for 4, sometimes 5 hours continuously.
I've sat through some brutal college lectures, but 5 hours is a hostage situation. The accounts from the audiences are wild, though. People reported leaving these lectures feeling exhausted but exhilarated.
The raw energy he projected was undeniable, but many attendees admitted they couldn't actually follow the complex, nonlinear web of geometry, structural physics, and philosophical cosmology he was spinning. He frequently invented his own vocabulary on the spot, using portmanteaus like synergetics and tensegrity.
Which makes it hard to peer review his thoughts.
Exactly. It raises a vital question about how paradigm-shifting science is communicated. Was his real value found in the strict mathematical rigor of his engineering? Or was his true value his ability to act as a catalyst, inspiring a new generation to look at the world geometrically?
Whatever his methods, his core philosophies seem incredibly prophetic today. He had this mantra of doing more with less, which he called ephemeralization, using the inherent strength of geometry to build lighter structures that require a fraction of the raw materials. But he also had a very stark warning about the direction of human knowledge. He argued that overspecialization is dangerous.
Yes, and he used evolutionary biology to prove his point to his audiences. Fuller noted that if you examine the biological fossil record, almost all known cases of extinction stem from a species becoming too overspecialized.
Give me an example of that.
So a creature adapts perfectly to one highly specific environmental niche. Maybe a bird evolves a highly specialized beak that can only eat one specific type of flower.
Okay.
But when the climate shifts and that specific flower dies out, the creature's overspecialization has destroyed its adaptability. It can't eat anything else. It goes extinct.
And he believed human scientists were doing the exact same thing intellectually.
He did. He believed humanity was hyper-specializing its academic and scientific fields. We were creating brilliant biologists who knew absolutely nothing of architecture, and brilliant architects who knew absolutely nothing of physics. By isolating our knowledge into silos, he argued we were losing the comprehensive geometric understanding of the whole system.
Which feels like a perfect segue into another massive debate highlighted in our research. It might seem like a mundane argument over semantics on the surface, but it actually proves Fuller completely right. It's the crisis of terminology in modern science. We are so specialized, we don't even use the same words anymore.
This is a critical issue today, particularly in the fields attempting to apply natural geometry to human engineering. We have terms like biomimetics, biomimicry, and bioinspiration floating around in the literature constantly.
To the layperson, they all sound identical, copying nature to solve problems.
But our sources feature a rigorous meta-analysis conducted by researchers Tim Huber and Jörg Mussig. They reviewed over 1,000 scientific abstracts across these fields.
Let me guess. They found that scientists have no idea what the other scientists are talking about.
Essentially, yes. They found a staggering level of ambiguity and contradictory definitions. One researcher's strictly defined biomimicry is another researcher's loose bioinspiration.
And what's the real-world implication of that?
The implication is severe. Without precise, universally agreed-upon definitions, the interdisciplinary collaboration that Fuller championed completely breaks down.
Right, because if an architect wants to build a skyscraper that vents heat like a termite mound, they need to collaborate with an entomologist. But if the architect's engineering software uses a completely different definition of biomimetic structural load than the biologist's data, the collaboration fails.
Huber and Mussig point out that this linguistic ambiguity actually leads to deeply flawed study designs, duplicated efforts, and massive wastes of research funding. It is the exact danger of overspecialization. We desperately need a shared language to connect the specialists.
And maybe that shared language isn't English or Latin or technical jargon. Maybe that shared language is pure geometry. Because when we move into the third phase of our exploration today, the frontiers, the cutting-edge discoveries that might change absolutely everything, we see scientists completely abandoning complex equations for pure geometric shapes.
Prepare yourself, because we are about to delve into what is arguably the most significant, mind-bending breakthrough discussed in our sources today, the amplituhedron.
The amplituhedron?
Yes, discovered by physicists Nima Arkani-Hamed and Jaroslav Trinka in 2013. It has the potential to fundamentally rewrite our understanding of reality.
Okay, I want to take this slow, because when I read this in the notes, I had to reread it 3 times just to grasp it. Let's set the stage. What problem were Arkani-Hamed and Trinka actually trying to solve?
They were working in quantum particle physics. At facilities like the Large Hadron Collider, Researchers smash subatomic particles like gluons together at nearly the speed of light. They want to calculate the exact probability of what will happen when those particles crash and scatter. These predictive probabilities are called scattering amplitudes.
And historically, how did we calculate those? I assume it wasn't easy.
It was a mathematical nightmare. For decades, physicists relied on Feynman diagrams formulated by Richard Feynman in the 1940s. These diagrams are used to mathematically map out every single possible path and interaction the virtual particles could take through space and time during the collision.
Which sounds straightforward enough for two simple particles.
For a simple interaction, yes, but in the quantum realm, as you add even a few more particles, the complexity explodes exponentially. For an interaction involving just a few gluons, calculating the scattering amplitude requires drawing hundreds of separate Feynman diagrams, and that translates into dozens or even hundreds of pages of extraordinarily complex continuous equations involving tens of thousands of mathematical terms. It was a mathematical brute force method. Even massive supercomputers struggled under the sheer weight of the calculations.
So it's a chaotic, computationally heavy mess. Enter the amplituhedron. What did these two physicists actually discover?
They discovered that you can completely bypass the hundreds of pages of Feynman diagrams, and you can entirely ignore the tens of thousands of mathematical terms. Instead, you can calculate the exact same scattering probabilities using the geometry of a single, highly complex, multidimensional geometric object, the amplituhedron.
Wait. You're saying they replaced 100 pages of calculus and time-based particle tracking with a shape?
Exactly, a multidimensional shape. I want to make sure the magnitude of this breakthrough lands for you. The amplituhedron reduces thousands of dynamic, time-based quantum interactions into the physical volume of a single geometric structure. You simply calculate the volume of the amplituhedron, and that volume gives you the exact scattering amplitude.
Just the volume of the shape?
Yes. It is a staggering, beautiful simplification of the math.
That is mind-blowing. But here's where the research gets deeply philosophical and, frankly, a little terrifying. The massive implication of the amplituhedron is what it says about the fundamental nature of our reality. Because, as the sources point out, to calculate the volume of the amplituhedron, you do not use the variables of space or time. Space and time literally do not exist in the math of this object.
This suggests a profound tectonic shift in cosmology and physics. For over a century since Albert Einstein, we have viewed the four-dimensional fabric of space-time as the foundational canvas of the universe. Everything happens within space-time. But the amplituhedron implies that space-time is not fundamental at all.
Are you saying Einstein was wrong? If time isn't real, why am I aging? How can a geometric math equation prove that time is an illusion?
It doesn't mean time and space don't exist in our human experience. It means they are emergent properties.
Emergent properties? Like what?
Think about temperature. Temperature is not a fundamental property of a single atom. One atom isn't hot or cold. But when millions of atoms bounce against each other, the property of temperature emerges. The amplituhedron suggests that space-time is an emergent byproduct of a deeper, purely geometric reality that exists entirely outside of space and time. Quantum interactions aren't happening inside space-time. Their underlying geometric interactions are generating the illusion of space-time.
Our sources use a really fascinating analogy to ground this. They describe the amplituhedron as a digital or discrete model. It takes highly complex dynamic systems, things that involve growth, decay, movement, wave interference, and represents them completely statically.
Yes, outside of time.
It's like taking a beautifully complex, action-packed movie and realizing that the entire plot, emotion, and timeline can be perfectly understood by looking at the stationary facets of a single, intricately cut diamond.
That's a beautiful way to put it. And this brings us full circle to the philosophical work of Samit Kumar, which is heavily featured in the sources. He draws a direct, unbroken line between this cutting-edge quantum breakthrough and the ancient sacred geometry we discussed at the very beginning.
The torus and Metatron's cube.
Right. Just as the ancients believed the flower of life represented the hidden universal order, the amplituhedron represents the ultimate cosmic blueprint at the quantum level. It is the hidden geometry of reality, finally made visible to us through advanced mathematics.
So physicists are finding this geometry at the subatomic scale. But what I love about our research today is that while quantum theorists are looking at microscopic shapes, architects are using the exact same principles to build our modern cities. Let's look at biomimicry in 21st century architecture.
It's incredible to see the scale change.
We are literally taking the math of biology and blowing it up to the size of skyscrapers. Let's take a tour around the globe using the case studies from the sources, because they are stunning.
A phenomenal starting point is the Metropole Parasol in Seville, Spain. If you look at it, it is an enormous, sweeping, undulating wooden structure that provides shade over a massive public square. The architects didn't just design something that looked aesthetically pleasing, they drew direct structural inspiration from mushroom morphology.
Wait, they built a city square out of mushroom designs?
They studied the cellular structure and the support of lamellae under a mushroom cap. To replicate this on a massive scale, they utilized a material called laminated veneer lumber, or LVL. By mimicking the microlamination naturally found in fungi, they achieved an extreme strength-to-weight ratio.
So it's light, but incredibly durable.
Exactly. This allowed them to build a massive, sprawling canopy that seemingly floats above the city, supported by surprisingly few foundational pillars.
That's incredible. Moving from mushrooms to the ocean, let's talk about the ICD-ITK Research Pavilion in Stuttgart, Germany. The researchers there looked at the exoskeleton of a lobster. Now, a lobster's shell has to be incredibly tough to protect it from predators, but it has to be lightweight enough to allow the animal to move quickly.
Nature solved this through structural anisotropy. The lobster shell is made of layers of cheat woven at highly specific, varying angles, depending on exactly where the shell needs to be rigid and where it needs to flex.
So it's not just a solid block of armor.
No. And the researchers in Stuttgart used advanced robotics to weave miles of carbon and glass fibers in the exact same geometric multidirectional patterns as the lobster shell. The resulting pavilion is incredibly lightweight, but boasts a structural integrity that traditional steel and glass construction would struggle to achieve efficiently.
And then in Austria, we have the Hungerberg funicular stations designed by Zaha Hadid architects. These transit stations sit in an alpine environment, and the design is deeply inspired by natural ice formations and glacial flows.
Hadid's team studied the fluid dynamics of freezing water. The flowing organic geometry of the thermoformed glass roofs mimics the way glaciers naturally drape and freeze over the rocky landscape.
We're blending right in.
Yes, it's an architecture that doesn't fight its harsh environment with rigid, flat boxes, but rather harmonizes with the natural geometric flow of the mountains while still serving as a highly functional, weather-resistant transit hub.
I think my absolute favorite example, though, is the Swiss rebuilding in London. Most people know it as the Gherkin. It's that towering, bullet-shaped glass skyscraper designed by Norman Foster. It looks incredibly futuristic, but the entire structural concept is actually based on the biology of a sea sponge.
Specifically, the Venus flower basket sponge. This sponge lives in deep ocean environments where water currents are incredibly strong. Its exoskeleton is a complex, geometric lattice that perfectly diffuses the massive force of the water currents, preventing the delicate sponge from being crushed.
And the architects realized that deep ocean water currents act a lot like high-altitude wind currents in London.
Exactly. Traditional, blocky skyscrapers act like massive sails. The wind hits them flat, creating enormous structural loads and dangerous downward vortexes at street level. The Gherkin uses the exact same geometric lattice as the sea sponge.
So the wind just slicks around it.
Right. As the powerful London winds hit the building, the circular lattice structure geometry naturally diffuses and spirals the wind around the building. This drastically reduces the structural load, and it also creates natural pressure differentials that the building uses for passive internal ventilation, massively reducing its reliance on artificial heating and cooling systems.
It's just brilliant. And finally, we have the Esplanade Theater in Singapore. If you've seen it, it looks exactly like two halves of a durian fruit sitting on the bay. Has a very distinct, spiky, armored exterior.
But those spikes aren't just decorative architectural flair. The theater utilizes a complex system of triangular aluminum sunshades that mimic the biological spikes of the durian.
Why do that?
Singapore is incredibly hot and humid. The geometry of these shades is designed to respond dynamically to the sun's angle throughout the day. They provide optimal shading, cutting out the harsh glare, but still allow natural light to filter in. It's a geometric adaptation that regulates the building's internal temperature organically.
So we are taking the hidden math of mushrooms, lobsters, ice, deep-sea sponges, and tropical fruit and turning them into skyscrapers and train stations. And the expert consensus in our sources notes that we are only at the very beginning. The real frontier of this field is combining these natural geometric shapes with next-generation technology. We are currently integrating biomimicry with artificial intelligence, creating digital twins of these buildings to run millions of wind and solar simulations. We're using large-scale 3D printing to manufacture these complex organic structures right on site.
But visual physical architecture isn't the only frontier where this geometry is being applied. We must also consider how this math translates back into sound and how sound can actively construct physical space. This brings us back to the acoustic philosophy of Iannis Xenakis. Xenakis was a rare polymath. He was a brilliant structural engineer, a mathematician, and a revolutionary avant-garde composer.
His work is where the lines between all these disciplines just completely dissolve.
Yeah.
In the early 1950s, he composed an orchestral work called Metastasis. And he didn't compose it the way Mozart or Beethoven did.
No, Xenakis largely abandoned standard musical notation. He composed Metastasis using architectural drafting paper.
Wow.
He graphed out the complex mathematical equations of hyperbolic paraboloids, these sweeping, three-dimensional curved geometric surfaces. He then assigned those mathematical curves to the string section of the orchestra.
How do you play a math curve on a violin?
The violinists and cellists were executing continuous glissandos, sliding their pitch up and down to perfectly map the coordinates of the graph. The musicians were literally playing the acoustic geometry of a building.
That is insane.
Yeah.
He turned a math equation into a blueprint, and the blueprint into a symphony. But it goes even further, because a few years later, Xenakis was working as an engineer in the studio of the famous architect Le Corbusier. They were commissioned to design the Philips Pavilion for the 1958 World's Fair in Brussels.
And Xenakis achieved the ultimate synthesis of the cosmic code there. He took the exact same mathematical equations, the same hyperbolic paraboloids he had used to compose the music of Metastasis, and he used them as the structural blueprint for the sweeping, tent-like concrete walls of the pavilion.
He proved that you can take the mathematics of a soundscape, fluidly transforming over time, and freeze it in place to create a physical building. The math of the music literally became the math of the building.
It is the perfect demonstration that geometry is the universal translator. Whether it is expressed as a sound wave, a concrete wall, or a quantum scattering amplitude, the underlying blueprint remains completely unchanged.
Which really forces us to look at the broader human implications of all this. We've covered Section 1, the foundations, Section 2, the debates, and Section 3, the frontiers. Let's move into our final section, the implications. What does all of this mean for ethics, for economics, and for our society as a whole?
This is where we return to Samit Kumar's philosophical application of the amplituhedron and sacred geometry. It's one thing to say the universe is made of math. It's another entirely to ask how we should live our lives based on that knowledge. Kumar argues that human life, whether you're looking at the struggles of a single individual or the complex dynamics of a massive corporate organization, is full of dualities, conflicts, and competing interests. He describes the path of human progress not as a clean, straight line, but as a chaotic, zigzag path.
And he uses the physics of wave interference, which we talked about earlier with cymatics and recording studios, to explain human behavior.
Exactly. Just like sound waves can crash into each other in a poorly designed room and create destructive interference where they cancel each other out, or constructive interference where they align and build each other up, human choices interact in the exact same way. Our actions are energetic waves that physically impact our collective reality.
So, to translate this into organizational terms, is Kumar essentially saying that when different departments in a company or different factions in a society have wildly conflicting goals, they are creating destructive interference?
That is a perfect translation. Kumar's thesis is that modern society is currently bogged down by this destructive interference. We are plagued by shifting political narratives, relentless blame shifting, and a chaotic desperation to preserve the status quo at all costs. To survive this chaos, individuals and organizations must actively align their thoughts, intentions, and actions with what he calls a sacred design.
And sacred design here doesn't necessarily mean adopting a specific religious dogma. As I understand it from the sources, it means aligning your actions with a higher transcendent purpose that benefits the whole of the system, rather than just the selfish desires of the individual part.
It's about recognizing the interconnected topology of reality. We are all individual nodes in a shared geometric lattice. If one node acts entirely selfishly, trying to pull all the resources to itself, it stresses and destabilizes the entire structure. But if we align our actions with the harmonic geometry of the collective, if we seek symbiosis, much like the ecosystems Buckminster Fuller studied, we create constructive interference. We build a more resilient, harmonious reality.
That is a deeply powerful way to look at human ethics. But this concept of a universal geometric reality also extends far beyond human society and even beyond our own planet. Sources bring up the work of astrobiologist Paul Davies, specifically his book, The Eerie Silence. Davies explores the search for extraterrestrial intelligence, and the prevailing fundamental question in that field is, if an advanced alien civilization exists out there in the cosmos, how on earth do we talk to them? We don't share a culture, we don't share a biological history, and we certainly don't share a spoken language.
But we do share the universe.
Yeah.
And if the universe runs on math and geometry, then geometry is the ultimate cosmic Rosetta Stone.
That gave me chills when I read it. The implication is that alien intelligence might not try to communicate with us using radio broadcasts in English or even binary code in the way we expect.
If an alien civilization has mastered the physics of their reality, if they have built advanced spacecraft and harnessed stellar energy, they almost certainly understand the principles of the amplitude. They understand the golden ratio, the thermodynamics of the torus, and the tessellating structures of space. Davies implies that this geometry could be the universal language. Across the vast, silent stretches of the cosmos, intelligent life is likely connected not by culture, but by the shared realization of this exact geometric truth.
It is awe-inspiring to think that the same geometry a sea sponge uses to survive in the ocean might be the exact same geometry we use to decipher a message from a distant star system. But to bring it back down to a deeply human, practical level, the sources also explore how we can interact with this geometry in our daily lives right now to improve our own physical and mental health, specifically through the practice of sound baths.
Yes, this is where theoretical quantum physics and the mathematics of cymatics meet personal, biological well-being. A sound bath is a meditative, immersive experience where participants are enveloped in sustained tones and acoustic vibrations, usually generated by precise instruments like crystal singing bowls, gongs, or tuning forks.
And reading through the research, this isn't just about listening to a relaxing playlist. There is a deeply physiological mechanism at play here, based entirely on the geometry of sound we discussed with Hans Jenny's vibrating metal plates.
Oh.
When you're immersed in these specific sustained frequencies, it induces a phenomenon called brainwave entrainment.
Right. The brain is an electrochemical organ. When it is exposed to strong external rhythmic frequencies, it physically shifts its own internal electrical patterns to match or entrain to the external stimulus. The specific geometric frequencies used in sound baths encourage the brain to downshift from the high-stress, alert, and anxious beta state into the relaxed alpha state, and eventually into the deep meditative, restorative theta state.
Furthermore, we have to remember the physical composition of our own bodies. We are predominantly water. We are over 60% water. And just as the cymatics experiments showed water and sand physically organizing into perfect geometric mandalas under the influence of sound, the water inside our own cells conducts these geometric sound patterns incredibly efficiently.
The biological implications are profound. When you are in a sound bath, the harmonic geometry of the sound is physically rippling through the liquid medium of your cells. The sources point out that this mechanical vibration promotes healing at a cellular level. It stimulates the vagus nerve, allows for deep emotional release by calming the amygdala, and helps clear physiological tension. You are quite literally tuning your biological instrument to the harmonic geometry of nature.
It is a staggering realization that the self-organizing principles of the universe are not just out there in the cosmic microwave background or hidden inside a particle collider in Switzerland. They are actively, physically shaping the cellular structure of your own body in real time.
It bridges the gap between the macrocosm and the microcosm perfectly.
Which brings me to a final provocative thought to leave you with, something to deeply mull over as you go about the rest of your day. We have seen, across every piece of research today, that the very fabric of our reality is dictated by the exact same mathematical patterns. We see the golden ratio dictating the twist of the double helix in your DNA, and we see the acoustic perfection of the golden mean shaping our rooms. We see the biological biomimicry of lobsters and mushrooms shaping our modern skyscrapers. And we see that all the way down at the absolute quantum level, the chaotic variables of space and time entirely dissolve into the pure static geometry of the amplitude. If all of this is true, if the universe is essentially a self-playing, geometrically perfect instrument, are we humans truly the grand architects of our world? Or are we simply the biological instruments through which the universe is playing its own geometric symphony?
It is a humbling and exceptionally beautiful question. I would strongly urge you to start looking for these patterns in your own daily life. It changes the way you see the world. The next time you see the Fibonacci spiral in a simple pine cone, or the hexagonal lattice of a honeycomb, or the structural proportions of a classical building in your city, recognize that you are not just looking at random biology or clever human engineering. You are looking at the direct manifestation of the cosmic architecture. You are looking at the hidden code of reality itself.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. To our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us on Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.